No, first, yesterday I explained some way to write down the wild-type character formula, which I call Brion. And I want today start with writing, no, actually some formula, but in the finite version, and maybe it more related with geometry later, but now it is just formula. Anyway, my data was the following. So now I have lattice, and I consider this a kind of polytope. But this formula which I want to write is for finite version of this. So it means that I have points just labeled by 1, 2, 3, and so on till n. Yes, and just from the point of view of pure combinatorics, it means, well, that I have polytope and A1, A2, and so on, AN. They have to be, as usual, non-negative integers, so AI bigger than 0, and AI, yes, plus AI plus 1 is less than k. K is control of the size of a polytope. Anyway, right now, because n is fixed, it is just finite number of such kind of points of the convex polytope. And as usual, I'm writing the character type things by all possible A, and here I have still the sum of AI and Q sum of I times AI. And these are things I want to determine. Yes, and no, actually this, now it is polynomial in two variable, and for that there are many formulas actually. And the Brion type or Weyl type formula, it is looking by the following way. It is summation. But first of all, let me say that because of some reason, combinatorial and geometric also, the formulas let us think that n is even. Otherwise, formula is similar but slightly more complicated. Yes, and well, it is equal to what? We have to sum by two numbers, m and n, where m plus n is less than n over 2. Yes, and here we have the following things. On the top, just monomial like this, km plus n. And here we have q, and on the top we have quadratic form. K always in the top, then we have m square plus n square. Yes, and how it is written, we need to have, no, first of all, like this, and here n plus 1 times n. Yes, and as usual in such kind of formulas, parameter k is only here. And downstairs we have some factor. And this factor is the product I equal 1 to m, 1 minus qi, and 1 minus q minus I minus here, m plus 1, and here we have that inverse. Yes, and it is not all. We have also here product I equal to m plus 1, here n minus 2n small, here 1 minus qi z, product I equal 1 to n, 1 minus q minus I, and last term is 1 minus q minus n plus I plus n minus 2 z inverse. Yes, and so this is all. No, formula, no, in principle people can write down longer formula than that. But, and surely if it can be misprinted here and I can make up mistakes when I rewrite it there. But anyway, what is the structure of this formula? Then it is just how I explained yesterday that I have polytope which is living in n-dimensional space. And it is given by inequalities of like that and this one. And I want, on this polytope, I have function, which, I calculated on the integer point on this polytope, but it is a sort of discrete integral. So this function depending in z and q, and it is here. Yes, and no, actually, to be a character of something, and maybe I'll explain in a moment what is this. But from the point of view of Brion, how it is going, that we take, yes, no, the ideology of Brion is following, that we have polytope, we have vertices, and we can put a person on each vertices who calculate the character in the vicinity of these vertices, and then sum up it. And about Brion actually give this answer for more complicated function here, and this function depending in a, it cannot be arbitrary, but at least if you follow Brion, it can be the function. So here, what is the structure? There are some kind of exponential function. It is z, some linear function of I, q, some different linear functions. In principle, I can add here some q1, the sum of ai square I, for example. or some other linear function, and in this case, Brion saying that the procedure is working. Yes, but if we, the good things about some small choice that we have only two linear functions of this this function in I has degree 0 or 1. And in this case, it is possible to take in account only some distinguished vertices. And such vertices are, in this case, are k0, k from one side, and k0, k from other side, and many zeros in between. Yes, and in this formula M, how many k's I have from one side, and N is how many k's I have from other side, or opposite, I don't know who is M, who is N, but actually it is like that. Yes, and so in some sense, no, it is not good explanation why actually it is working, but we need vertices which I concentrate near one end of my segment or in other end. And we need an even, because I want to have k0, k0, and so on. It is some distinguished things, and but no, it is surely the question was to do what to do with this. But if you really do, and the structure of the formula will be that. Anyway, now let us discuss a little bit. No, before I return to vertex operator, algebra, business, and so on, what actually we computed. So it is surely just combinatorial, but let me say the following. Well, so this kind of thing, so if k equals 0, then it has to be equal 1. So it is, maybe because of misprint it is not, but actually it is sum of rational function, and the sum has to be equal 1. Now, what is going on if k, no, if it is k0, but k equal 1, such kind of they are labeled bases in what? So we can take C, E minus 1, E minus 2, E minus 3, and so on. Yes, and first of all, no, it was in our infinite business, but now I have only n here, so it means that it will be stop in n. I have a polynomial ring just in n variables, and after that I factorize it by quadratic relations, and such kind of quadratic relations are the sum of E alpha, E beta, alpha plus beta equal to some I. Yes, and here alpha beta is from here, and so this the biggest element which I factor is if I is equal or smallest maybe First one is e minus 1 square, and the last one is e minus n square, and they are monomials, but all others are not, so I make up such kind of factorization. Yes, and then such kind of configuration give me a monomial basis in this quotient well, and it is some kind of theorem. Therefore, it means that I take this and calculate the character. And character is, again, let me just repeat what is going, that on this polynomial ring we have two grading. One, z grading now is degree of this polynomial. And second, q grading, it means that each ei here, e minus I here have q degree I. So it is just different degree, and surely such kind of relation are homogeneous with respect to both degrees. So from this point of view, it is fine. And after that, let me just say what kind of geometry is hidden in such kind of consideration. If I want to describe geometry, maybe first let us return to the case when n equals infinity, but it will be the same story in general. Well, I have now let us fix some k1, and in this case my space like this for bigger k is what? It is now it will be c a minus 1, e minus 2, and so on, but I factorize it by maybe still k here, the sum of e alpha 1, e alpha 2, and so on, e alpha k for plus 1. If k equal 1, here it is k plus 1 here, and alpha 1 plus alpha 2 plus so on plus alpha k plus 1 is equal to some j, and for any j we have factorization. So this gives me some algebra, and let me denote this algebra by ak. And in this case, because it's appear from geometry, from representation of SL2 hat, then we can found the following. Let k be equal k1 plus k2. Then it is possible to write down, first of all, just a map. AK goes to AK1 times AK2. I want to say that it is rather evident homomorphism of algebra which sends this to this. And actually this is even embedding, but it's not so clear. But about map, it is going by very, very usual formula. So here we have generators EI, and here we have generators EI first and EI second. It is from here and from here. And we can say send this EI just naively, and it is working to EI1 plus EI2. Yes, and No. First, what is easy to check now? That here quadratic relations are holding, so actually why? Because if we write down generating function as usual, Ez is the sum of ei z minus I, then what is this? So Ez is going to Ez times 1, wow, to 1 times Ez. And after that, we can make up simple calculation and just look where Ez times k plus 1 is going, and just using binomial theorem, this in power k plus 1, we see that it will be 0. So therefore, the image here satisfy such kind of relation. Therefore, it means that by this simple way, we know what is going on. So each A itself is algebra, but let us forget for a moment about this structure of the algebra, and let us just look to this. And so we can take the sum of a k bigger than that, and we have co-multiplication, and because of evident reason it is co-associative. So this guy is co-algebra. No, and each we have grading, and so we can go to graded dual spaces. And by this way, we get some commutative algebra. And this commutative algebra, no, if you have graded commutative algebra, so we have many grading, but now what I can do, I can take the sum of AK star. No, better to take it in graded sense to avoid infinities. By K, it is graded algebra. It is infinite dimensional, all things yes, but still we can take projective spectrum of this. We expect, and really it will be some kind of projective algebraic manifold, and then and as usual, so we expect what? That such things will be some manifold M, and because it is a projective manifold, we have here some line bundle which is maybe O1 or something like that, like on projective space, and we can consider the key power of it and homology of this, and no, we can, by such construction we cannot be sure at all, but in reality, because of it in this special case, such kind of line bundles have only zero cohomology, and so we are living in the world of projective geometry, and by the way, all kind of such calculation, how they are going. Well, we take this manifold, but because we have Z grading and Q grading in each component, so it means that we have the action of two-dimensional torus on this manifold, and after that we can apply the algebraic geometric technique and so on, looking for fixed points and apply Lefschetz type formula and so on. No, Lefschetz later, but about fixed points, it is possible to say something now. Fixed point, they are give, with respect to torus on this manifold, they give us functional on a space of sections, surely. And it means that they give us the element from the dual space, from this. And if you look, what is this from the point of view of configuration space, it will be our extremal vectors. So it means that algebraic geometry knows something about this polytope and knows who is who there. So it means that, again, that these special vertices corresponding to fixed points and all other vertices from algebraic geometry, they do not correspond to a point of manifolds at all. They are surely living in a dual space, but such functional does not belong to our manifold. And this is, no, it is, no, such kind of arguments cannot be proofs, but it is not far from that. Well, now, no, our situation with n, it is the same things, but we just cut all this e, just factorize it by e with number less than minus n. But even after that, let me put n here, and here, and n here. It does not affect this phenomena. Again, co-multiplication, again, such map, and so on. Now, a situation from algebraic point of view even better. Then we have finite number of variables, and then it gives me, as a result, even better object, which is really finite dimensional manifold in this case. And one more thing, and so you see that the structure of this formula just saying that we can make up the manifold and looking for fixed points, and in this case, if I cut it labeled by m and n, and this formula gives us the just contributions of these points. And before going further, one more comment. And no, co-algebra, yes, but the question, what can be the reasonable or handleable model of commutative algebra, the sum of k, a k star? I return to the case when n is infinity. And so again, if k equal 1, then my space, let me write it again, e minus 1, e minus 2, and so on, and I factorize it by quadratic expression, which I do not want to write again, but what we can say about dual space. Well, it is a good way to understand the dual space by the following. So we make a factorization, and this is the space of polynomials 1 is, no, just 1 maybe, or I don't know, maybe this one. It is just 1 from this polynomial, and surely it survives in factorization. Yes, then we have space E minus 1, E minus 2, and so on. Yes, and the question is who are they, and we and anyway I want what I really want. I want dual space, and if you are talking about dual space can be no, this space, how it is written, it can be identified with z minus 1, z minus 2, and so on. Yes, and we can understand them as what? We have z inverse, and factorize it by z. And after such factorization, we just have space with such kind of basis. And if you write down it by this way, then it is more or less clear what is the dual space. Dual space to this is functions is one form, dz, which are just regular. So this is this object is one form, and if I want to calculate pairing of this with this, I have just product and take residue, and so such kind of one form. Yes, and no, if we look to second degree, so in the second degree we have the space E minus 1, E minus I, E minus J, I and J here, but we have to factorize it by our quadratic relations. Well, and after that, what is going? When we factorize, if we not factorize, then it will be symmetric, second symmetric power of this, and dual space before. So by the same reason, it is very natural to identify with object like this. No, notation are bad, but I do not know a different one. So this thing is symmetric power of this. So it means that this dz1 and dz2, we understand it is not two forms at all. They're symmetric with respect to z1 and z2. And no, because it is confusing, so better just to erase this and this, and just to bear it in mind that they have to be there. Anyway, but it is dual space for this before factorization. But after factorization, dual space has to be subspace here. And what is this? It is very clear, because a structure of our relations is very, very simple. It is E alpha, E beta. So dual space is just subspace here, which has 0 on the diagonal. Dual space is just space of such sort, and no, actually it is clear, because if we take this function without this before, restricted to the diagonal, and take Fourier component, it will be functional here, and it will be just this. So, so this is going on, and so let me erase this, and so this is the condition that it is 0 if Z1 equals Z2. Yes, and then surely what is reasonable to expect really occurs. So if we go further and considering the polynomials here component of z degree s, so it means the polynomials of s degree of this, then dual space to s component will be f, z1, z2, and so on, zs. They are surely symmetric because all is symmetric here, but they have to be 0 if z1 equals z2. Yes, so in this case it is possible to write down here. All this is, I think it is easy to see, yes, but it is possible to understand a little bit more, how to say, not physically, but from vertex operator algebra point of view. Well, in our space, I mean, what is A1? In my notation, it is all this space. Acting operator EZ, which is as usually generating functions. What we are doing if we go to a dual space, we take functional psi here, which is going to C, and after that we calculate the following. I take 1 here, just 1, then I apply EZ1, EZ2, and so on, EZS, and take functional with this psi. Yes, and no, psi is functional and E are series, but as usual we can write down this, and as I explained, such kind of things has to be Laurent polynomial, but in this case, because E are starting with -1, it will be, if follow our convention, not Laurent polynomial, but usual polynomial. And our condition that EZ square is 0 just means that corresponding polynomial have to have 0 on the diagonals. Yes, and no, actually this is just different way to repeat the same arguments. It is so the same story. Yes, what is not completely evident even in this case, but very easy, that if we have polynomial psi, and polynomial psi gives me actually the collection of S should be different. But if psi is homogeneous in evident sense, that only it will be non-zero if we have number of E is equal to degree of psi. Yes, and it is also more or less evident that such kind of things is a function which satisfies this condition. What is not completely evident, that we can find psi, such we can get any functions which is 0 on the diagonal. Now, in this special case, it is not big deal, but what is going on if we considering bigger k? If we have bigger k, then our relation is EZ power k plus 1 is 0. And in this case, it means that as a result, we again get polynomials in Z1, Zs, but condition now is surely related with K, and the statement is symmetric if Z1 equals Z2 equals so on equals Zk plus 1, it has to be 0. And because of the same reason, then we get functions of such sort. Now, using this, we can describe the algebra, which is the sum of a k star. And so, so let me write what is this. So k is 0, we have 1, and if we go for k1, k2, and so on, if we have some k, so what we have in degree k? Now, in degree k, we have as grading, so what we have here is the sum of the following space. It is just constant, functions in one variable, function in two variables, and so on. They are all symmetric polynomials, and because they are living in this column, it means that such kind of functions they satisfy these zero conditions. So if x1 equals x2 equals so on, if k plus 1, then it is 0. Now, surely it means, so on this space we have this grading, it is z grading actually. And it does not affect it till level k plus 1, but after that, spaces of function become less because of this condition. And after that, well, because this is dual space, then no, because of my co-multiplication and so on, I expect to have a product here. And what is this product? So right now, my structure, at least by graded. So I can take something here and something for different k and calculate the product. For example, if k is 1, then product is going from this to that. So from here I have function, suppose, in s variables, which are 0 if x1 equals x2, and symmetric one. So it is s component here. And I have function g, x1, and so on, xt. No, again, the same story. It is 0 if two variables. And after product, I want to have function f times g, but now it is living here, and this degree also sum up. So this function have to depend in x1, x, s plus t. Yes, and if you do this, no, because if you just write what I said and translate it to this language, then you have what? It will be f x1 x s times g x s plus 1 and so on x s plus t, but we want to get symmetric function, and we need to put symmetrization in all variables here. And as a result, no, people who knows, so it is very simple version for shuffle product, and shuffle product is in more complicated situation, surely, but spirit is the same, and what is going on is also the same. But right now we get some symmetric polynomial in all x's, yes, and surely this is living in this column, because if here you take x1 equal x2 equal x3, then what is possible, but at least one pair of this will be here or here. Then this condition is held, and as a result, we get some algebra. Well, so this is explicit things now. We have description of my algebra, and we can ask about the projective spectrum of corresponding projective manifold. And again, that if we return to this, so if I consider n, then as I'm saying that now situation is better, and better in the sense that all spaces will be finite dimensional, and how we can see this n in this construction. Well, when we are talking in language of A, it means that we factorize by e minus n minus 1, and we just remove all e with, and if I go to a dual space, then what I expect, it has to be subalgebra here. And such kind of subalgebra also very, very simple to say what is this. We have to restrict ourselves just by function x1, xs, maybe. No, by degree it means that for some k we have in S component functions in S variable which satisfy this zero condition of k plus 1 points we substitute. But because we want subspaces, that it is very easy to say what is this. This function in this smallest subalgebra has degree in each variable less than, I think, n minus 1. Maybe it's mistaken. Yeah, I think it is correct. Surely, if you calculate the product, this restriction remain true, and as a result, you get some smaller algebra, and about this algebra, maybe I move too slow, but nevertheless, it is. I think it is important to. In this case, what we have in k equal 1? No, in k equal 1, we have what? We have constant, then we have polynomial in one variable such that degree is less than n, maybe less than n, not n minus 1. then we have function in two variables, x1, x2, with the same condition, and so on. Yes, first of all, it is clear that corresponding space will be finite dimensional, because conditions are rather strong, and we cannot, if you consider the polynomial of many variables, that because it is 0 on the diagonal, it has factor xi minus xj squared. Yes, but because we have degree restriction, if number of variables is too big, so it's impossible. Yes, and it is very easy also to check that in a case, from the case of our combinatorics, we have configurations, and in one is just one, then if we have only one point, it can be here, 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 and here, and dimension is equal to this. If we have pairs, then it is dual space of polynomials which are degree, which are 0 on the diagonal, and you can easily calculate how many. It will be some binomial coefficient. Yes, and if you find this, how many configuration you have, so because we have condition that ai plus 1 is less than 1, then it means the same story. If we have cross here, we cannot have cross here and here. So this is Fibonacci condition, because if you add point, it satisfies usual Fibonacci recurrent relation. So as a result, you get some algebra which is in degree 1 dimension is Fibonacci number, and then actually this algebra is generated by what we have in degree 1, so it is some algebra which such set of generators. Yes, and maybe it is all about this, but it is rather natural to add then here no dimension is Fibonacci number, but it has grading. If you consider only Q grading, what you get as a result is Q Fibonacci number. If you have Z and Q grading, then it will be also graded Fibonacci number, and you see that in this case, such kind of formula give you some expression for Q Fibonacci number, for Q Fibonacci polynomial, maybe, which has such form. Okay, and maybe that's all, but maybe one more thing. No, about Lefschetz fixed point formula, I have to talk a little bit later, but the structure of Lefschetz fixed point formula is what? That usual situation, we have fixed point, and contribution of fixed point usually have the same structure. Some monomial divided to a product of such kind of factor, and this formula was follow from Brion, and it means that it is we get it combinatorially. But if we have, we expect that the corresponding manifold which we are talking here is smooth. And no, the point is that maybe I confused about even or odd n. For one n, it is smooth, really smooth. If I'm not confusing, what I'm saying is true or opposite is true. for n is even, it is smooth. For n is odd, it is almost smooth in the sense that they have only one bad point, where it is not smooth and it is more complicated structure. And because of that, such kind of formula is good for even n and slightly worse with odd n. And actually, Brion also sees this. Okay, now also some comment about the constructions of such type. No, here it is some playing of commutative algebra which we can construct by shuffle product and things like that. But really, we derive it from some kind of vertex operator algebra, which in this special case is just L.2 hat of level k. Yes, and comments is how much this construction can be related with vertex operator algebra structure. But again, that maybe it is good to say one thing, that, well, what was my semi-infinite construction? So I had, for example, C, E minus 1, E minus 2, and so on. Yes, and factorizing by relations for k equal 1 for simplicity, and it was my space W0. And also, what was it? In this space, I just repeat, I have vector E minus 1, and so how to write it? So suppose in this space it is 1. First I act by operator E minus 1. This vector is here, but first relation that E minus 1 square is 0, so I cannot go further. And second relation, E minus 1, E minus 2 is 0, so it means we have not E minus 2 here, but first vector, which is going on, E minus 3. And because it is E minus 3, so what generated by this vector is C, E minus 3, E minus 4, and so on. Yes, and relation is the same, so E minus 3, and so on. And in my notation, this is W2 maybe, or minus 2, I do not know, maybe minus 2. Yes, and because of this construction, we have such map where 1 is going to this vector, and I claim, and even ask people try to prove it, that this is embedding. And now if you go to a dual space, then we have W0 star, and it is going to W minus 2 stars. Yes, and how it is going? Yes, and the way is more or less clear. So what we have here? We have 1, and we have function in 1 variable. We have function in 2 variables, and so on. Yes, and here we have also 1. We have function in 1 variable. We have function in 2 variables, and so on. But the difference is that no, it depends a little bit how to write it. But you see that in my convention it is just polynomials, and here we have x1 minus 2. No, because this is a structure of dualities. Here we have z minus 3, z minus 4, and so on. Yes. And dual space to this is no, 2 maybe here. No, I want to say what is a dual space to this. And because it is, no, dual space has to be smaller, and I think this is correct. And here we have x1 square, x2 square, and so on. And about the map, no, for example, map from this to this, it is clear. So f x goes to f0. Yes. Map from this to this is also clear. Then it means that we have this object is function in 2 variables, x1, x2 times x1 minus x2 square. And I also have to substitute x2 equals 0. Then I get x1 square here, and it is going to this. And this way is going on well. So my space, semi-infinite space, on this language is this inductive limit, and dual space has to be a projective limit. And no, you just have to take projective limit of all these maps, and structure of map for k equal 1 is simple. I have to just substitute such x1 equals 0, and this is my map. And well, and construction is construction. It is, I just repeat what I said, but maybe it is reasonable to say that such kind of view, it is rather non-precise, but dual to this semi-infinite construction can be realized in a space of symmetric polynomials of infinite number of variables. But surely the meaning of this infinite number of variables you can see from this. So, for example, this is 1, here it is f, then this f is a restriction to something in 2 variables and 3 variables and so on. Yes, and maybe this 2 is not correct, but anyway, what is this? This is f. It is function in one variable. Here we have function in two variables, and here x1 minus x2 square. Yes, but here I need to have, I think, x1 minus 2, x2 minus 2, something like that. Maybe I am wrong, but some element from here is going on to this, and so on. I'm moving to infinity, and so this is a description of my space, which probably can be useful somewhere. But I never saw, I do not know the good usage of this description of dual space. But again, this is dual space to vacuum or non-vacuum representation of SL2 hat level 1, as I said. So from this point of view, it has to be good. Yes, and now now let me say what just I want. I mean the semi-infinite construction and vertex operator algebra. Well, about vertex operator algebra things, I more or less, maybe slightly in confusing way, maybe not, but I said that in a case of fermions, or in a case if we are talking about Clifford algebra, then I said that we had the following construction, that I have had in principle any algebraic curve, and in my first lecture, if I put several points, maybe 3 points, P1, P2, P3, in each point, then I can put representation. It was W, again I always P1 times W P2 and W P3. Yes, and again the logic was that these three spaces in some sense are talking with each other, and curve determines the functional to one-dimensional space. C, but how much we can identify it with C, this other question, but at least it's one-dimensional space. And the structure of vertex operator algebra, this is more or less this. But first of all, what is talking, what we I explained for this Clifford and so on, such kind of functional exist and can be rather easy to determine through this co-invariant with respect to some Lagrangian subspace, and it is very easy to see the existence of such things and so on. It is possible to say that vertex operator algebra just generalize this construction, but first of all, for generic vertex operator algebra, such kind of things does not live for any genus. So vertex operator algebra, naively, this is what? It is a structure which formulated for CP1 only, And we want the following data. First, we have some vector space, which is calling vacuum representation, which is name of this is vacuum representation of vertex operator algebra. First, for Clifford, it was rather natural way to put such kind of vertex vacuum representation to a point. And in general case, we need the same story. I can put, I need some machinery how to do it, but it is not very complicated, but at least we need something. To each point P, we can put vacuum representation of my algebra in a point P. But main ingredient of a structure, that if we have several points, does not matter how many. Then we can, we have some functional to C. And physical logic, or physical, maybe in something quasi-physical language, saying that we have CP1. We understand CP1 is like this, maybe, yes, and we can put vacuum representation here, vacuum representation here, vacuum representation here, and they are talking through Riemann surface, which I draw here. No, it is some kind of construction, and this map have to satisfy some associativity condition. And this is more or less hidden here. So for that we need the following. If I have this, I can interpret it as a map to vacuum P3 star. Yes. And after that, part of structure, we need to have some kind of identification of this, which is not dual. After that, we interpret such kind of story as a product, from this to this to this. Yes, and it has to be associative in some natural way, and if yes, then we have vertex operator algebra structure. And if you see axiom of vertex operator algebra, they are doing something like that, but in more complicated way. So it means that it is something like this, and if we write down this as the algebraic structure, so element from here, product to element here is going to this, then surely it depends on what is going on here, and it is some algebra, but properties are rather subtle if you want to formulate it in a pure algebraic way. Anyway, but my question now is following. Suppose such kind of my message is that semi-infinite constructions give you vertex operator algebra. Yes, for that we need to do the following. We need I have, suppose CP1. I have several points. And my representation, suppose for k equal 1, k equals 0, 1, it was, and in this case, when I started with relation EZ square equals 0, it was something like this. W minus 2 embedded to W0, embedded to W2, and so on. It is like that. So the limit may be big W depending in P. Then I put this space here, here, and here. And then I need this map. WP1 times WP2 times WP3 to see and what kind of construction it can be. And no, because of no, I want it is third lecture, and I want to say at least something about topology invariant of three-dimensional manifolds and so on. Let me formulate it as a problem, but for people who need it. But problem is, let me say, what kind of answer? Well, a construction is following. I have CP1. I have some number of points, Pi, and I put, as I said, W in a point Pi. Now, according my construction, no, who actually, by construction, who is acting on this WPI? In this WPI, we have action of EI, and no, first of all, it is not good. Let us put M here, M belongs to Z, such, and they satisfy condition EZ square equals 0 in this case. Yes, and then no, in WPI acting also, as I said, shifting group Z, or on this direct limit is acting only even part of this. But in my construction, which I want to outline a little bit, actually I can use, but in the simplest version I can avoid it. I do not use it. But I need a little bit more. On WPI, we have the essential grading. No, this essential grading, it means that W pi I is equal to the sum of W pi I. It is some L here. L belongs to Z. And the main property of this grading that each EM acting from W L pi I to W L plus 1 pi I, and just E add some grading. Yes, and one, no, I think it is correct. So in W0, for example, we have vector 1, and if I construct this, I think that the degree of this vector has to be 0. It is, no, W0 is explicitly described as C E minus 1, E minus 2, and so on, up to this, and it has element 1 here. And this element 1 is surely some distinguished element from this, and is one of extremal vectors. Then degree of this extremal vector has to be equal 0. I think no mistake is this. Then after that, I can formulate the theorem construction. Construction is following. Well, we have, no, actually, any Riemann surface, but I restrict myself only by CP1. Yes, and I have W P1 times WP2 and so on, this W some PS. Now, first of all, on this each the question is that by definition W it is something where operators EM are acting, and the question is who are they? To put W on Riemann surface on CP1 just means that we can say who are they. And the generators of this algebra EM just see the inverse, where Z is local coordinate in P1, for example. No, for construction of W, actually, we do not need the explicit identification, ZI. We do not need, actually, the choice of local coordinate. It is one point of a story. Yes, and better to say it by the following way. So we have our curve E, and K is field of rational functions on E, and EP is completion of space of a rational function with respect to norm, which is corresponding to this point P. So it means that P in a local coordinate is just this. And such kind, if you will return to my construction of W I define in terms of E, but actually it is possible to say it by this way. So just functions, so W pi I is a representation of functions on a small vicinity, on a small vicinity of this point. In my notation of first lecture, it was dpi. Maybe it was like that. It is puncture, infinitely small puncture vicinity of this point. So, well, again, in my construction for Clifford algebra, I used also linear bundle, some bundle, but in this case, this bundle is first one-dimensional and second is trivial. So I can do this. Therefore, if I consider the tensor product, then we have the action of k pi 1 plus k pi 2 plus k pi s on this product. And again, the co-invariant logic is following. I can take my curve E minus P1 and so on Pn to C. They are rational functions with poles here, and it is some O regular function on this. And I surely can embed it here just by, I have function and then expand it here, 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 and I have a collection of these elements. Yes, and so these three space, S spaces are talking through that. So I can take co-invariance with respect to action of O, E minus all this. And I get something, but it is not the answer what I want, but almost. I'm saying that in all these spaces, as I said, we have grading, and we have grading in this case, in this space, and just sum of grading here, 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 and here. Yes, and next element of construction, I have to take this space of co-invariance and calculate the degree 0 of this, and theorem says that it is one-dimensional space. And it is this after that, in this sector, it is one-dimensional space. It gives us functional on this product, and so it is actually reproducing the structure of vertex operator algebra on this space. Now, if somebody want to really try to do it, maybe it is good. No, maybe some student, I do not know. It is good to consult with me to do. Actually, you take co-invariance, considering dual space, and dual space in some degree has interpretation as symmetric functions just by the way which was appear here. And we, the question is that we just have to put here, no, it is inductive limit, yes, but I can put here Wi, Pi1, Wi1, Wis, Pi(s), and then when you calculate co-invariant and go to a dual space, then you just have a version of this construction with functions. And after that, the problem is just to count. Now, it is interesting to count it in all degrees, but in some degree it is 1, and it is nice property of the situation. So, well, I want to say more about this because I like this construction very much, but maybe it is good to stop and go to some next subject. And the next subject, maybe I only started today, but name of this subject is the following: Q graded tensor products and vertex operator algebras business, and also the not invariants appear here. Anyway, what is the problem which I want to talk now? Well, if we have some Lie algebra SL2, yes, we can take finite dimensional representation and no, even C2 times C2 n times maybe, yes, and then I can decompose it. And for example, we know that no, surely I can decompose it, but I can consider even before decomposition. I have here operators E, H, and F. Operator H give us some grading, and the dimension of this is 2 power n, m, and the dimension of grading component is binomial coefficient. Yes, and yes, and a graded version of this is rather natural in a sense. So in many situations, in many parts of mathematics appear Q binomial coefficients, and Q version means that from the point of component, it means that we have some component here, and it has dimension of binomial coefficient, but and the character of this, so it means that if I take trace of z power h, then on this tensor product, so what it will be? It will be the sum of zi I starting from maybe minus m to plus m, and here the coefficient, it will be some binomial coefficient, and it will be the character of with respect to the action of h. Yes, and so for C2 times C2, so what is this? It is to write this correctly, it is z minus 2 plus 2 plus z2, and if you have just C2, then it is z minus 1 plus z1. Yes. So I write this not very good way, but the usual story is this. And if you have 3 z2 times c2 times c2, then we have z minus 3 plus 3 z minus 1 plus 3 z1 plus z3. So they are characters of with respect to this. And q character, zq character, it means that each binomial coefficient here we have to replace by q binomials. Maybe also take care about q power, which I also probably discuss later. Yes, and then first, no, q binomial is natural things, but how it can appear here? For that, we need C2 times C2 times C2, and we need to have here not only z grading or operator h from SL2, but also something more than that. We need some operator which can be denoted by L0 because it is related with a generator from Virasoro, and it has to produce q grading in this space. Yes, and why this is important, for example, from the point of view of knot invariants and things like that? Because knot invariants, they appear through Jones as traces of some, so Jones, we have the action of braid group, which is acting there. We can take element and, for example, calculate trace, and it gives me invariant of knot. But such kind of situation in general, it is complicated, but sometimes you can choose braid by such way that the corresponding operator give you some operator surely depending in Q, and it gives you some grading on a space, and this grading is related with what I'm talking about now. No, it is very rough description of situation. Real situation is not so simple, at least. But it is something like that. And the question now is, and also just to say this a little bit more, that for example, if M is even, then we can decompose and find out how many times trivial representation appears here. It is surely well known that this number is equal to Catalan number, and so we get simple. No, Catalan is Catalan, and it is has many gradings, but at least one of them can be constructed through this. So my goal will be to discuss a little bit several ways to introduce such grading and to discuss the relationship of this grading with the structure of vertex operator algebra business, and also it is good to say also one last generic comment, that people, if you have C2 times C2 times C2 many times, then such a kind of story appear in lattice integrable models. So it means that C2 times C2 times C2 it is some space where something which is calling transfer matrices is acting, and transfer matrices is cooking up from Summer matrices, quantum group action, and so on. Yes. But from the physical point of view, such kind of story have to describe some field theory, actually two-dimensional field theory. And after that, if number of C2 become bigger, we want in a limit find really such field theory, but field theory is complicated, but after some simplification, we want to find conformal field theory. Conformal field theory, from a mathematical point of view, we want to do something with this and try to find some mathematical construction which produce vertex operator algebra from that. And the question how to do it and what is the relationship of such kind of construction with what actually physicists want, it is a good question, but at least something can be done, and this is also a story what I want to talk about. So my subject, sub-subject maybe, or something like that, so graded tensor products and affine Schubert variety, and for that let me first to say the following. Well, I did not explain that in details, but well, I have this situation which we are talking all time today, k equals 0, k equals 1, k equals 2, and so on. Yes, and in a construction of manifolds, I had C e minus 1 and so on till infinity, and then factorize it by relation depending in k. And so I had, how was it, e0, e1, e2, and so on. And here I have co-algebra structure, and a dual space I have algebra structure, and then it is I can considering projective spectrum of this. Yes, but what I did not mention, and maybe I need it now, that in my notation, so what was this? But it is surely C, it is W0 maybe, but for k equal 1, it is W0 for k equal 2, and so on. There are such kind of constructions, and we have a co-multiplication map that W02 is going to W01 times W01, and I explained how. But what I want to mention now that my semi-infinite business, I change this number, and I can put here 2, 4, and so on, and just go to a limit. And construction of co-multiplication is compatible with such limit also. So it means that I can take the semi-infinite limit, it is, and I have a map from wk1 plus k2 to wk1 times wk2. Yes, and no, all objects are rather huge now, but nevertheless, it is also co-algebra and so on. And I can go, after some work, surely to a dual space, and it gives me, and also it can go to the projective spectrum. And this projective spectrum in this construction will be what people are calling the Grassmannian affine Grassmannian for SL2. Yes, and it is some kind of construction. So at least if we go to a little bit more standard setting or notation, so what I construct here, here, and here. So actually it is vacuum representation of SL2 hat of level k1 times plus k2. This is vacuum representation, and maybe standard notation are for that from SL2 hat L0 k1 plus k2, and here is L0 k1 times L0 k2. Yes, and so what is going on? That from this point of view, we are living in this affine Grassmannian, and all kind of consideration with these small pieces, and even with when I have such kind of finitization, I mean the formula which I started today. It is also saying me something about geometry of the corresponding flag manifold, so in some sense I am living here. And no, I hope people knows at least something about this affine Grassmannian business. But let me just recall maybe main definitions and what is going on here. So if you are talking about affine Grassmannian, that first you have a group SL2, and here I can take the inverse. So this is just by 2 by 2 matrices, and coefficients are element from this field. Yes, and here I have subgroup which in this language usually calling the maximal compact. It is SL2C. Yes, and so then definition of affine Grassmannian is just quotient SL2C Z inverse by SL2C yes, it is some. No, this can be understood as some kind of manifold, but surely right now it is just very symbolic. I have some group and infinite dimensional. I factorize it by some subgroup, and what kind of manifold we get by this way, but at least some geometric intuition it can be here. And from this, and now, because it is almost time to be over, let me just say what is the relationship of what I am talking here with the business which I discussed today, yesterday, and so on. Well, no, this is some group, but here, for example, I tried at least to describe all story, even this vertex operator story, only in terms of E, of some kind of E. And who are these E here? So let us consider subgroup which is looking like this, and here is F. Now F is the element from C, the inverse, and suppose F, yes, and if you considering the Lie algebra of this group, that it will be 0, 0, 0, and some G. So F, G in both cases are just element like this. Yes, and what else? Then for SL2 group or algebra, that does not matter, affine, we have a conception of Weil group. And Weil group is a semi-direct product of the 2 over Z, and then what? Again, the details, maybe more details tomorrow, but on this Grassmannian manifold, the Cartan group is acting. And so, as usual on Grassmannian manifold, we have fixed points. And if you are talking about flag manifolds, then fixed point, at least in finite dimensional case, labeled by while group. And here it is Grassmannian, it means that it is a little bit smaller manifold. And fixed point are labeled by just Z. And so our structure is the following. I have this Grassmannian. I have fixed points. Which are labeled by Z. Then I can take any fixed point and act to this. No, because it is homogeneous space, I can act by this group. So it gives me something like this. Some submanifold. There it is infinite dimensional. And again, naively, I can take a closure of it. It gives me some manifold which is a part of my story. And I want to say that what was written here from the beginning. So I had this e minus 1, e minus 2, and so on. I factorize and construct some algebra and then consider the projective spectrum of this. But this is just closure of such kind of orbit inside the flag manifold. Maybe I explain a little bit more tomorrow how, at least, how to think about this. Anyway, flag manifold from this point is looking like how to say, the orbits of nilpotent group, sometimes they are calling by semi-infinite cells. And actually two different things are usually calling semi-infinite cells, but they are. And so on this flag manifold, we can take extremal points and act by nilpotent group and consider the closure. And so in this case, we have such infinite book structure. Smallest manifold, it is more smaller, it is bigger, 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 and altogether it gives me some kind of realization, or version, better to say, of a flag manifold, or Grassmannian. And this is what we are talking now, and maybe it is also in the beginning of next lecture about this flag manifold. I just start with some simple explanation how to think about it and how to understand the Schubert decomposition of this and so on. Yes. And after that, we go to the direction which we want, to this great tensor product. Fine.